Hello friends and welcome back. In this video we'll be talking about rolling motion, arguably the most famous and studied application of this composite motion we talked about that has a translational element and a rotational element. And now what is rolling motion? As you you can probably imagine what it is that I'm talking about. If you have a surface and an object that is rolling along this surface, rolling without skidding, especially, is what we're talking about. It means that this has a sort of global velocity, and in particular we care about the velocity of the center of mass, all right? And at the same time is rotating. And so if we were to follow kind of the path of a single point on its circumference, this would do something like this and like this, etc. All right. So if you can try this at night, you stick a little light on your bike tire and you try and focus on the light as somebody is cycling, then this is the trajectory that you would see. Okay. The goal for us today is to relate the translational motion of this of the object as a whole, which is dictated by its velocity and potentially its acceleration, linear acceleration, and the rotational part. These are not in rolling motion. These are not just independent things. They have to be related by a specific connection, and the specific connection is simply the fact that the distance traveled by the wheel or the cylinder, whatever your rolling object is none other than r, the radius of this, well, either its cross section or the wheel, if it's a wheel, multiplied by the change in angle. This is a reflection of the fact that the arc of circumference that is spanned by an angle phi is simply r times phi, right? So look at this. Let's call this d, let's call it delta x, because it's the change in position x of the center of mass of the object. And so if delta x is r times delta phi, then in a certain time delta t, let's take it either very short or let's take a constant motion, constant type of rolling motion, what we get is that this is true, so it's r delta phi over delta t, and we have names for these, and that's that velocity is r times omega, all right? Which is maybe unsurprising, and you've seen this before, but notice that the situation we encountered this formula before was when we were studying uniform circular motion, and we were asking, okay, what is the velocity of a point on its on the edge of the circle, on a circumference? And we discovered that indeed the speed was r omega. It was the radius times the angular velocity. This is a similar situation, but what we're talking about is that this v is the velocity at which the wheel itself is moving, wheel or rolling object more in general, is moving along, okay? And so this is what I meant to say when I said it's not an obvious thing that any object that is both rotating and moving translationally has this relationship. This is a specific property to rolling motion. exclamation mark. Okay, very nice. Ooh, one thing before I forget. So another special property of rolling motion is that, again, so let's look more closely at what type of combination of translational and rotational motion we have. So for, let's say, a pure rotation, what we have is a circle, and if you keep the center of mass fixed here, then imagine that this is your angular velocity, then a point here will have a velocity v, vc center of mass, let's say, namely omega r, and a point at the bottom, so the one sort of touching the road, as it were, will have a velocity that's minus omega r. Nothing new, nothing mysterious here. The pure translation motion of another wheel that instead collectively is moving forward at a certain speed omega r is that each point, I should have drawn them the same length, of course, all of these points are together moving forward or to the right with a certain velocity. And instead, the rolling motion, which is the combination of these two, see, look at what's going on. We have these three different situations where the center of mass is moving at the velocity it had due to rotation, which is 0, plus the velocity due to translation, which is omega r, and there you go, omega r, which is the velocity of the center of mass. The point at the top is moving with the velocity due to rotation plus omega r, plus the velocity as a result of translation. So that's twice. Maybe I'll try and make this drawing a little nicer. So this 2 omega r for the point at the top. And what about the point at the bottom? It's the velocity due to rotation, which is negative omega r, plus the velocity due to translation, which is plus omega r, and this is motionless. So instantaneously, the point that is touching the ground is at rest. That is the precise definition of rolling motion. Because if this velocity wasn't 0, but either positive or negative, it means that that object is actually sliding on the road. There's a component of sliding or skidding and not a perfect rolling. You can see this also in this drawing here at the top, where, see, when that point I was considering hits the ground, momentarily it's at zero velocity. Right. This is the pure sort of special property of rolling motion. The point that is touching the ground of this rolling object is motionless. Very nice. Next page, and let's see if we can say something about the kinetic energy of an object that is rolling. Okay, so take an object that has a mass m and a moment of inertia I. Okay, and this is my object that is rolling. So given these, the total kinetic energy of an object like this, as we said before, is the sum of the translational part, which is 1/2 mass times the speed of the center of mass squared, And there will be the rotational component, which is I omega squared. Moment of inertia and angular velocity squared. Right. Now, I can rewrite these, since I had this relationship that the velocity of the center of mass is none other than, or the speed of the center of mass is none other than omega r. I can rewrite this as 1/2 mv of the center of mass squared. We rewrite this as before, but we write this one as I, and look, c velocity of center of mass squared divided by r squared. And so I can factor out the v of the center of mass squared, actually, that multiplies this sum, m plus I over r squared. Beautiful. I could do the same, but replacing v instead of omega, and what I would find, so this is in terms of, let's write it like this, in terms of v of the center of mass. So if that's the number that I have, that's the easiest way to calculate the kinetic energy. If instead I have omega and the radius, obviously that has to be known, then I do the same thing or a very similar thing, and I find that it's m r squared plus I. Okay. Try it. You basically replace the value for the value for v in this here, and that's what you find. Very nice. So let me zoom out a second. I'm gonna rewrite this up here, or yeah, actually maybe not even. I'll just highlight this. So K total kinetic energy. And let me show you, because it's nice to, it's a cute little thing to see it explicitly. We said that rolling motion is one where the point of contact with the road is momentarily at rest. Right? We said that this is v equals 0, that there's a v center of mass, aka omega r, of the globally. And so if we split this motion into its translational part plus rotational part, we just discovered the expression for the kinetic energy. But we could also see this momentarily as a rotation of this object, okay, that I'm sort of coloring in, around this pivot, right? And then it's a purely rotational motion. Again, look, it's not rotating about the center of mass or anything like that, but it is, it's rotating about this point. See, in a way, locally or momentarily, it's as if this ball or this, wheel or cylinder, whatever it is, was here, and then in the next instant you could imagine it would be here, and then here, and then here. So turning around, pivoting around this this point in the middle. Okay, and we can ask, all right, what is the kinetic energy associated with this type of motion? Let's find out. Well, it would be a purely rotational motion. So this would be 1/2 I times omega squared, where I, this moment of inertia, is not the moment of inertia around the center of mass, but instead, due to the parallel axis theorem, we know that I is equal to the center of mass value plus the mass of the object times the distance between the two axes, and this distance is none other than a distance squared. It's r squared. So all in all, what you have is 1/2 the I of the center of mass, or of an axis that runs through the center of mass, plus mr squared times omega squared. And will you check this out? That's exactly what we wrote down up here, where we had solved this or found this expression by calculating the combination of the translational and rotational component. And it's wonderful that we find precisely the same result, as we should, but with a different sort of conceptual interpretation of instead a purely rotational motion pivoting around the contact point, and calculating like that using the parallel axis theorem. Very, very nice. Okay, this was rolling motion. Hope you enjoyed it. Thank you so much for watching. I'll see you soon.